We've defined matter in a few different ways, written down in a few different ways. We see different ways of defining it in different books that we might look at. And today we're going to sort of take a different perspective on that. Today we're going to talk about states of matter. So anything that is in a state of matter must be matter. And for our purposes, we're going to worry about solids, liquids, and gases. We'll talk more about that in a minute. So what we're going to do is we're going to take the things that we can see in the everyday world or in the laboratory, and we're going to talk about what that means is happening to the little particles that make those things up. So we're going to relate the macroscopic to the submicroscopic particles that are in a substance. Again, for our purposes, matter is going to be solids, liquids, and gases, and we probably have a pretty good idea of what's a solid, what's a liquid, what's a gas. We can pick something up, take a look at it. We have a good feel for that. We have some experience with that from previous science classes. Now there is a fourth state of matter called plasma. And plasma is very hot gases that start to break down into charged particles. Plasmas do exist. In fact, the sun is mostly plasma. It's not solid, liquid, or gas. But we're not going to worry too much about plasmas. We're not going to think too much about them. We're certainly not going to observe any plasmas in any of the laboratory work that we do. So we're going to stick to the solids, liquids, and gases. So here's one way to look at those things, solids, liquids, and gases. And this is a slide that comes from NASA, the Space Administration, that part of the federal government. And in each one of these little drawings we have the same substance, the same sample of the same substance represented as a solid, a liquid, and a gas. So we know that a solid, when we place it in a large cube here, the solid will hold its own shape. A solid doesn't take the shape of its container, and that solid has a fixed volume, at least at a constant temperature. And even if the temperature changes, the volume of a solid doesn't change very much. So here's an example of that. Here in this beaker, you might be able to see we have a rock. It's an odd-shaped rock. It does not take the shape of the beaker. And if we take it out of the big beaker and put it into a smaller beaker, we can see that it doesn't even fit. There's no possibility that this is going to take the shape of the container that's in. This solid holds its shape. And that's what we're talking about in this description. Now, a liquid does take the shape of its container. We know that when we pour a liquid from one container to another, if the two containers are different shapes, the liquid changes shape. But the volume of a liquid doesn't change, even if we shift it from one container to another, at a constant temperature, that is. And even when temperature changes, the volume of liquids doesn't change a whole heck of a lot. So here's an example of that. Here we have a flask, sort of a conical shaped flask. This is an Erlenmeyer Flask. It's got this green, it's just water with green coloring in it. And we know that if we take this conical shaped liquid, pour it into this cylindrical shaped beaker, that the liquid takes the shape of the new container. The liquid did not change volume when we did that. A gas is, on the other hand, will expand to take the shape of its container when we put it into a big container. So, in this drawing of the solid, all the particles that make up the solid, even though they're not shown in the drawing, are close together. And the same for the liquid. The particles that make up the liquid, they aren't in the drawing because they're all close together. But this drawing of a gas is showing us that when a substance is as a gas, the individual particles of that gas, they might be atoms or they might be molecules, are independent of one another. They move far apart from one another, and so they're able to independently move until they fill up all parts of this large cube that this substance is in. So the gas takes the shape of whatever container that it's in, and it takes the volume of whatever container that it's in. If we took the gas that's in this drawing and put it into yet a bigger cube, the gas particles would move to all parts of that cube. They would take the shape and volume of the new container. So here's another way to look at these things. Now in these drawings we do have individual particles, and the individual particles are represented by the circles. So in a solid we can see that the particles are close together. They're attracted to one another. And oftentimes in a solid they're attracted to one another and in very organized patterns. So you can see that these are lined up in columns and rows. And these particles are in fixed positions. Because they're attracted to each other so much, they don't tend to move around a lot. Now they do move a little bit, and these arcs, or parts of circles that you see in the drawing here, are intended to show you that these particles are moving a little bit. For a solid, that usually means they're just vibrating around a fixed point. So when we add energy to a substance, and oftentimes we do that just by heating it up, so we add energy to a solid, and where does that energy go? It starts to make the particles move a little bit more. So in this drawing of a liquid, we now have some of the particles showing two part circles or arcs around them. That means the particles are moving a little bit more. So what happens in a liquid? In a liquid, the particles are not in fixed positions. We know that the particles are able to move with respect to each other. So we say a liquid flows. But the particles still stay close to one another. They still have a tendency to be attracted to each other. They don't have enough energy to go off and move around on their own. So if we continue to add some energy, and that's what our red arrow is showing us, we're adding energy. If we add enough energy to a liquid, we can turn it into a gas. And when a substance is a gas, the individual particles are moving so much on their own that they are not attracted to the other particles. They overcome, their movement overcomes the attraction. So these particles are moving a lot, and that's what the three arcs show us. And they're moving so much that they do not stay fixed or close to the other particles. So there's lots of space between the particles in a gas, and there's no organization at all to the particles. Every particle moves individually. Let's look at it from just one more perspective. Now, going in a different direction this time, solids on the right. So this picture here shows us a drawing, a representation of a solid. Each particle of this substance in these pictures has two atoms in it. You might be able to see there's two little spheres here. And when it's a solid, the particles are very close together and they're very highly organized. They're lined up in columns and rows. And again, many solids have particles that are highly organized. Not every single solid, but many solids do. So that makes a solid hard to expand or compress. Why can't we compress it or push it together? Because there's no extra space between the particles. Why can't we expand it? If we put a solid into a bigger container, why doesn't it expand? Because the individual particles are strongly attracted to each other. Here's our liquid. In a liquid, the particles are a little less organized. Their own movement is helping them move around a little bit, but they're still attracted to each other, and so they still gather in the bottom of the container. Presumably gravity is at work in this photograph here, as in this one here. So the particles stay close together in a liquid, but they can move somewhat. So liquids are also hard to compress and expand. Why can't we compress them? There's not much space between the particles. Why isn't it easy for a liquid to expand? Because the particles are attracted to each other. So just by changing it from one container to another doesn't automatically mean that a liquid will expand. And then here's a picture of a gas. And as we said before, in a gas, the individual particles have enough energy so that they overcome any attraction to other particles and they all move around independently. Gases are easy to compress because there's lots of space between the particles. And they're easy to expand because the individual particles aren't attracted to each other. So if we took this gas in this rectangle here and put it into a larger container, a larger rectangle, the particles would move around and they'd fill all parts of the new rectangle. So the gas would expand just by moving it to a new container. What happens when a substance changes from a liquid, a solid to a liquid to a gas, or a gas to a liquid or solid? That's called a change of state. Liquid, solid, gas are changes of, are states of matter. There are also phases of matter, so this is called a phase change, and these are physical changes. So when a substance becomes changes from a solid to a liquid to a gas, it's not that the chemical formula of the substance is changing. The individual particles don't change, but what the individual particles are doing compared to the others, are they attracted to other particles, are they moving, does change. And so that makes a change of state a physical change. It's a physical change. It's not a change in the chemical formula. All right, let's sum up our solids, liquids, and gases. First of all, solids. Solids have fixed shapes. The particles are fixed into position and they don't move around, and so the shape of a solid stays the same. And because everything's fixed in place, the volume of a solid doesn't change at constant temperature. And again, it's because the particles are strongly attracted to each other, and they're attracted so much they stay in their fixed positions. That makes solids hard to expand or compress. We can't compress them. The particles are already close together. They don't easily expand because the particles want to stay close to each other. They're attracted to each other. And the reason they can stay close to each other is that each particle has a relatively low amount of energy, so they don't have enough energy to break away from the other particles. What about liquids? Liquids, we know, do take the shape of their container, but they don't change volume when the temperature is constant when we shift things from one container to another. It's because the particles are attracted to each other, but they can move somewhat with respect to each other. So they don't move away from the other particles, but they slip and slide and flow. There's a word, they flow over each other. Liquids are fluids. Liquids are not easy. In fact, they're hard to expand or compress. Why? There's not much space between the particles. Can't compress them. And they're hard to expand because the particles in a liquid are still attracted to each other. They do move more than in solids, so we might say that the particles in a liquid have a medium amount of energy. More on average than the particles in a solid, but less on average than the particles in a gas. And we can sum up gases. They take the shape of their container, and the gas particles also move around to fill the volume of whatever container they're in. That's because the particles are not attracted to each other, or they have enough energy to overcome any attraction they may have to other particles. So we can say that these particles move independently. And that makes a gas easy to compress or expand. We can compress them because there's lots of space between gas particles, so we can push them closer together. They expand because the individual particles move independently of the other particles. So if we put a gas in a larger container, it moves around until it gets bigger. Gas particles, we can say, have high energy. They have enough energy in them to overcome the attractions between the particles. So there you have it. For our purposes, we're going to worry about 3 states of matter: solids, liquids, and gases. There is a 4th state, the plasmas. And the plasmas are going to be outside of our experience a little bit. So when we see something that is a solid, a liquid, or a gas, we now have an idea of what the individual particles are doing, and so we can explain the behavior of those things. And we also know that those things are matter. Have a good one.